So we continue the topic, which is ODE, ordinary differential equation, with a non-Lipschitz singularity. So just recall that we are motivated by behavior of partial differential equations where many systems blow up in finite time, so we get a singular state, which is essentially no Lipschitz for the equations of motion, and then after that time, or that finite time, so the finite time blow up, after that the solution becomes non-unique in some formulations, but sometimes we can recover the unique solutions with a regularization. So we are reconstructing this situation from partial differential equation in a simple setting of ordinary differential equations where the problem that the blow up will be just one point. And we will see that actually we already get a very rich picture which resembles many properties of partial differential equations. So what we do is we study this ordinary differential equation in finite dimensional space, and we consider the right-hand side singular at the origin. So we write it as R alpha Fy. So R is here is norm. Y is a vector on a unit sphere. So it's a vector of unit size. And then alpha is smaller than 1. So it's non-Lipschitz at 0. So at 0, 0 is a singular point. You can already see the derivative is infinite. Okay. So, and we specified this system a little bit more because this function f can always be split into the radial and spherical components. So f of y will contain a radial component, which is proportional to y, and spherical component. So this component is orthogonal. So it's point on the tangent to the sphere, which means, in simple words, that it's orthogonal to y. Yeah, so this is parallel to y, and this is orthogonal to y. So we just make an orthogonal decomposition. And then we considered new variables. New variable. You consider new variables that substituted r. So actually, it's convenient to introduce logarithm of r. R is positive, and so we can take logarithm. So it's z, and then we have new time. So what this logarithm does is when you're very close to the singularity. So when r is close to 0, then you're stretching the space. So logarithm is stretching the space. And then new time also introduced in the same spirit. So when we're close to 0, so we want to stretch the time. So when we're approaching the singularity, we want the time to be to change slower, and slower. So we never come really to the point in that new time. So what we do is we divide by r1 minus alpha. And so in terms of z, it will be minus 1 minus alpha z dt. So just put r is exponent of z. So this is what was our setting. And then the system, when we changed to these new variables, the system which was singular became regular. Yeah, so it does mean that the original system has regular solutions, but we can write solution in such variables that it becomes suddenly regular. So the rescaled system actually contains one dynamical system and a couple of integrals. So the main equation is that changing to the new time s, the equation for y becomes regular. So there's no singularity anymore. So you see, this is a dynamical system on a sphere. So remember that everything here is smooth, so the function f is considered to be smooth. So it's a smooth dynamical system on the sphere. So if you have a sphere, and so the vector y lives on the sphere. Point y is on the sphere. So it's y0, and then we can just solve this equation, and it gives you some trajectory which is on the surface of the sphere. So it means that nothing special can, nothing really bad can happen with the solution. Solution is defined for any time s. And whenever you get the solution, so you get a solution which is y is a function of s, and then you can reconstruct the rest. So the rest I will recall you how you reconstruct. So the z variable as a function of s is reconstructed from initial condition as an integral. So what you do, you have to take f radial component, compute it at the solution, and integrate. So this is how you get z. Well, automatically you get r because it's exponent, right? So it will be exponent of z0 will be r0 by exponent of the integral of r s prime ds prime. And then you get time, which is one more integration. This integration of what? Of exponent of this term, essentially. This is exponent. And you see, so we integrate t, so we put exponent on the other side, so it's minus will disappear. So time is obtained through double integration because there's one integral, and then another integral comes from here. So good. So this is the implicit form of the solution. Whenever you have any solution y of s, you can reconstruct also r. So from y and r you get x, right? Because x is a product. And then you have time, so implicitly you define the solution in original variables. So where the last free line is constructed using, so for this equation you just use y of s. So somehow you can think of it as sometimes it's called master-slave equation. So this is a master equation which is independent, and this is slave because it's just directly defined by the solution of the first. So that's how it works. So now, so now let's consider our example. So let's consider. Remember, we had an example we had an example yesterday which is two-dimensional. So two-dimensional, in that case, y vector is unit vector, so it can be written as cosine for cosine sine. And the sphere becomes a circle. Because in 2 dimensions, the sphere is circle, so it's unitary. So this is our S1. So, so y vector lives on the sphere, and we want to see how this works for this example. And we had very particular situation, so we considered f of y to be just that that original form, and f of r, I will just remember what it was. So f of r, so actually y is defined by the angle, right? So we can just write angle instead of y because there is one-to-one correspondence. So the fr was square root of 2 sine phi plus p over 4. And fs was minus sine 2 phi over 2. And then there was orthogonal vector to y, sine phi, cosine phi. Okay. So the next is that we need to find this equation. So this equation, so first of all, this equation dy ds, remember, so what? So it is dds of cosine sine, and if you just differentiate, it will be minus sine cosine d phi ds. And this should be equal to fs, right? So when you compare, you see that vector you can just cancel. So what you get is that d phi ds equal minus sine 2 phi over 2. So for the example that we consider, the equation, the rescaled equation has this form. It's a simple form. And it's obviously, so we can understand completely its behavior. The behavior is like this. So there are 4 points where it's 0, right? So 0, it's 0 here, 0 here, and then 0 here, 0 here, and then the other 2 zeros are on the side. So there are four singular points of this equation where the right-hand side becomes 0. And so what you can see is that he's minus, so actually the solutions are, so whatever is, this equation gives a solution which is like this. So there are 2 attractors, 1 minus 1, and whatever point you start, unless you start in this unstable fixed point, so whatever point you start except for this unstable fixed point, you will be attracted either to the left or to the right attractor. So there are 2 attractors. So there are 2 attractors. So the one attractor is phi equals 0. So phi equals 0 is this point, and we can compute what is fr. So fr if you put 0, this is sign that it's 1. Is 1, and remember that fr is a longitudinal direction of the vector field. So 1 means that it goes out. So this is a attractor. So whenever point is here, the solution will depart from the singularity. So we call this case expelling, defocusing. So it's defocusing, everything goes out of 0. And another attractor is pi, and then you can check that this is at point pi is -1, which means that whenever you're near this attractor, all the solution will go to the center. It's a focusing case. Focusing. So in a defocusing case, in other words, R will go to infinity. Will try to go to infinity. In the focusing case, R will go to 0, to the center. And indeed, this picture is in agreement with what we draw in a full plane. So in a full plane, this is just angular part, and then we can add it up together with a longitudinal part. So and the solutions that we had are like this. So there were solutions like this, and there were solutions of this form. Then there were solutions that. And there were solutions these are all solutions that we had, and you can see that angular part is indeed like this. So whenever you start on the left, you always move in the direction of this line, and when you start in the direction of this line, and eventually you approach 0. So this is focusing. And when you're on the right, you always, again, in the angle, you always start to approach the straight line, but at the same time you go out. So this is a relation between singular dynamics and the regular dynamics of rescaled system. And now we start with a situation. So what we can do is we start with a focusing attractor and show that it actually describes asymptotic form of the blow-up. So asymptotic form of blow-up associated with the focusing attractor. At the point pi. So what we do? So whenever we start with any initial condition on the left-hand side, it means that we started at some point y0 on a circle which will be attracted to this our attractor. So whenever you start on the left, for a regularized system, which is this, you're here, so you will be attracted to this point. Which means that as goes to infinity, so what we have is that phi will go to pi, right? So we'll come to that point, and y itself will go to minus 1, 0, right? So this is a point which corresponds to the pi, minus 1, 0. Okay, so now we know that at very large time s, y goes to the constant vector, which means that we can asymptotically compute all the rest. So let's start with z. So z, what happens with z? So z of s is z0 plus integral 0s f r y s prime ds prime. So we know that y goes to this number, and when y goes to this number, actually this phi, no? When phi goes to pi, the fr goes to minus 1. So this goes to minus 1. This goes to minus 1. So up to the constant, there will be some constant which correspond to the behavior before the asymptotic regime. And then this will be minus 1, so it will be minus s. So this is the asymptotic form of z, which is constant minus s. So the next is r of s. So r of s is just exponent of this whole stuff. Yeah. And it will be, you see, it will be constant. But now we take exponent, so constant will be a factor times exponent of minus s. And you already see that when s goes to infinity, so this goes to 0, right? As this goes to minus infinity, so this goes to 0. So we really approach the origin whenever we start from the left-hand side. And the last is time. So the time is one more integral. So we take this integration. Integral from 0 to s, exponent 1 minus alpha, z of s prime, ds prime. So now remember that this goes to the constant from here, minus s, right? This goes constant minus s. Constant gives just this prefactor, right? So this will be prefactor. Of integration. No, first of all, there will be two constants. The first constant will come because this integral, there will be some interval of time s when this asymptotic still doesn't hold. So this is the first constant. And second constant comes because z also contains a constant. So there are two constants. Constant 1, constant 2. The integral from 0 to s. And then we can just substitute e 1 minus alpha s with minus ds. So this integral, and this integral can be, we can integrate this function and give the same function with a constant which can be absorbed inside this constant. So let's write it. So this will be slightly different constant, no? Because we have prefactor here, but the exponent of minus 1 minus alpha s That's it. So there's no space, but okay. So let's write it again, and then we'll see what is the conclusion. So what we will do is we will call the first constant TB. So it will be TB plus constant by this exponent. So I will copy the two expressions. So this expression and this. So what we have is that R of S is asymptotically is a constant exponent minus S. And T of S asymptotically TB plus constant, different constant, of course, E minus 1 minus alpha S. Okay? And putting them together, what we see is that this R of S can be written as constant by R by TB minus T. And then we should put it into the right. Put right factor. So this is exactly what we wanted to find. So you see that the distance to the center, now we can remove this S because there's no S both sides. So we found we express the distance to the singularity through original time. Yeah, and we see it's finite time blow up. It's finite time blow up. So when T goes to B, TB, R goes to 0, and we know how, because we know the rate, how it comes. Because alpha is positive, or alpha is, remember that alpha is smaller than 1. So this is a positive number. Okay, so that's approach. So this is a asymptotic form of self-similar blow-up. Self-similar blow-up in the sense that there is only prefactor, and so there is a parallel prefactor, and then something which does not change. So in all the equations that you saw before, there was a function here. But here the situation is much simpler, so instead of function, we take a constant. So we only have a rate. Okay. So this is first possibility. So the next possibility is the question, so what are the other options? What are the other options? So the other options are related to different forms of attractors. So attractor is not necessarily fixed point. So we know that there are many other forms of attractors. For example, it can be periodic solution, it can be quasi-periodic solution, it can be chaotic solution, and so on. So these are other options. So the second options will be periodic attractor. Which means that y of S approaches some periodic solution. So as S goes to infinity, it approaches some periodic solution, which is obtained up to any constant. And what is this periodic solution mean that this yp of s plus period is the same as yp of s. And this is a phase, because when you obtain periodic solution, you don't know which exactly point you obtain. So it's up to the shift. So the graphically, of course, this is not possible or actually possible in a trivial way, but not impossible. Generally, you need high dimension. So for periodic solutions, you need high dimension. So periodic solution can already be arranged when x is in R3, which means that y is on two-dimensional sphere. So this is a sphere. This is a sphere. And what is here is that you take some initial point, y0, and then it moves on a sphere according to this, to our equation of motion. What is this equation? Yeah, to this equation of motion. Moves a sphere and it attracts to some, finally goes to some periodic, closer and closer to some periodic solution. So this is yp of s. So it approaches some periodic solution. Possible. So what it will be, what will signify that when you come close and so the analysis can be done in a similar way. So what you obtain is you obtain also the rate, but this constant will give you some periodically oscillating prefactor. Periodically oscillating actually in logarithm of this part. So I'm not going to see it, but anyway, it means that every time you come closer to singularity, you have something repeating. So you come closer to something repeats, something closer, something repeats, and it repeats in smaller times, small amplitudes, but in the same shape. So what this is an image, so it's certainly not, certainly conjecture. So you can remember this drop. Remember this drop, a droplet falling in water. Video. So we kind of what we see looks like blow up. So the droplet falls in water, and after the interaction, smaller droplet comes out. It falls already faster because it's smaller and jumps less than another smaller drop, and this happens many times. And actually, I think there was some paper, experimental paper, that measured this, and they concluded this is up to a period, it's a self-similar process. So it really looks like periodic blow-up. So, and the periodic blow-up is controlled by periodic attractor on this regularized system. And finally, you can also have a chaotic blow-up. Another option is chaotic attractor. So what does it mean? It means that, so this is already not possible on three-dimensional sphere, because on two-dimensional sphere, because the chaotic attractor only needs at least 3 dimensions to exist. So you need at least 4 dimensions here. So it means that D should be bigger or equal to 4. So the simplest version is are 4 and y is three-dimensional sphere. So just showing this schematically, to imagine this is three-dimensional sphere, not two, so there's one more dimension. So what happens is that you start with initial point, and then you start to go, and then at that moment, like for example, making this butterfly of the Lorentz system. So what you see is that again, if you try to continue the same analysis, you will get the rate of the same prefactor, but there will be not. But instead of constant, you will have a function which never repeats itself. So there will be some vector here, which is linked to the chaotic behavior. And this we also saw. This we saw. There are two cases which I showed. So one was a blow up in Euler on log lattice. And there we even saw what we even could visualize the attractor. So this was this chaotic wave moving. So we see this attractor here. And another was a blow up in collapse of universe. So this is Belinsky, Halatnikov, Lifshitz singularity. So I showed you some video in the past. So this is also a possibility. And what you can see is that though in Euler, of course, in general relativity, is something complicated, but you can reproduce everything on just simple ordinary differential equation. We just have one point singularity. And all this rich structure is already there for blow up. So for blow up means so how the solution will come to the singularity in a finite time if there is this non-Lipschitz property. Good. So the next. Traveling wave, so it's fixed point. So this is like fixed point, yes.
Just another function because it's infinite dimensional.
It's infinite dimensional, yes, but traveling wave is a fixed point. A traveling wave is analog of fixed point attractor. Essentially, you can even write it as a fixed point for Sabra model if you introduce Poincare section. If you introduce Poincare section, it will be just free. Fixed point of Poincare section. And actually for the shell models, you can for different models, you can make change them. There are models where you have periodic, you have quasi-periodic, you have chaotic, so everything can be. So in the shell model, just if you put a parameter and start changing the parameters, you can reproduce all the situations. And even see the bifurcations. You can see, so all these dynamical system pictures that you have the change from one, all these bifurcations are there, and these are bifurcations of blow-ups, of the blow-up behaviors. So that, in a sense, this ODE really reproduces what's there. Okay, so now the next question is after blow-up. So we got to the singularity, and we want to continue. And we know that we cannot continue in the usual way because there's infinitely many ways to continue. So we need to choose, to make a choice, because like we assume that in reality there is a choice. So we are, at least in the classical world, there is no The classical also, there should be something determined. There should be a solution. And the philosophy behind this continuation is that whenever we have a singularity in the equation which is not resolvable, you may think that the model is not that the model that you consider is not simply is not valid very close to singularity. So very close to singularity, you just forgot some features, and if you reconstruct these features, then the solution becomes unique. And this is what really usually happens. So what we think is, imagine that you have our system with a singularity at 0. We cannot pass through 0, but this is because everywhere our model is good, but very, very close to 0, we just forgot something. But very, very close, the rules change. So we have this but very close to 0, rules change. So, and they change in such a way that the singularity is resolved, right? So imagine that you have a corner, right? So you have a corner, and you throw the ball in the corner. You don't know which way it goes. But in reality, if you come very, very close, you see that it's not really exactly the corner. It has a structure, and it's actually not really singular. So when a ball hits, depending on the particular structure that you see very closely, it will know where to go. So this is our idea. So what we will do is we introduce regularization. So what you do is you define, you take small neighborhood. So this will be ball of radius nu around 0. And now we change our vector field such that inside the ball, such that it is smoothly connected to what is outside, but inside there is no singularity. We just make it smooth. And if you make it smooth, it means that whatever initial condition you take, it enters but exits, and you can continue. So there is no problem, because we removed the only problem that we could have. Since it's smooth inside, it exits. So the solution is now defined everywhere, at all times. And then we can, with a new positive. So how you usually do is you consider the regularized system, where the right-hand side is changed. And in our system, which has this self-similar form, so remember outside the singularity, it was this, but inside we take something different. And actually, in order to connect the two, what you do, you take a field which connects with F, but then the prefactor should be nu alpha, and here what you put is x over nu. So what this field does is that if it regularizes our f at 1 nu, then it regularizes for any other nu. It's just rescaled properly. So this regulation is valid with the same g for all nu. So it's kind of viscosity.
Does it change if the blow-up changes? It's not subsimilar?
No. Blow-up is for the outer part. And this is what redefinition of the field inside. So what will happen, the solution will want to blow up, But but before it enters to blow up, it will enter to this region where its rules changed. So it will actually avoid to blow up and go out.
No, it's just that if we know that our blow-up is not self-similar.
It's okay. It will go. It will come in some funny way and enter from some point, but continue.
But with the same realization.
With the same. No, this is fixed. This is fixed. So this is a model. This is a model, and then we see the solutions. Blow up is correspond to the solution. So our question is. This solution is always defined globally. So there exists a solution which for each nu there is a solution given initial condition, for each nu there is a solution. We can just solution smaller the nu, closer it passes through, but it still works. So the question is the limit. Do we have a limit when nu goes to 0 of this solution? So can we recover? So certainly when nu goes to 0, you collapse the center. So when nu goes to 0, if there is a limit, it will be solution of original problem, because it satisfies the original problem everywhere outside the ball, which means that if you collapse the ball, it will satisfy the original equation everywhere. So if there is a limit, it will be our solution. But the question, do we have a limit or not, in which situation? And how to characterize this limit? So, okay. Break. Okay, so let's continue. Where did we stop? Okay. So let's look at this a bit closer. So a bit closer with some, I will not give all details of the theory because you can, everything what I'm telling, you can see, you can formulate rigorously. So there is a, if you're interested, the paper is Derivas. Myself, nonlinearity, (2021). It's called Death After Life. No, Life After Death. Yeah, in differential equations. So we will see why. So essentially, so what we do? So we have. So let's just look at this situation a bit more closer. So just let's make a close look to this picture. So we are in d-dimensional space. I will always draw like 2 dimensions. So we have this small disk of size nu, and there is a solution coming in. So there is some initial condition, and then the solution comes in. It comes in through some point which we call, so radius is nu, so there will be, distance is nu, and y, there will be, the angular part is y entering, the entering value. Then there will be some dynamics inside, which is smooth, until it's getting out. So we will call this point y exiting, and then it exits. Right? So this is a picture. This picture, what will happen inside this very small region. So this somehow I assume that you arrange the field that any trajectory that enters exits. So that's. So what we have? So we have entering. And we have the entering, and then we want to understand what happens at x at time t. X at time t. But now remember that this part and this part, they correspond to this regularized system. So both solutions is y of s, but different y of s. So then they're connected. So this is a solution y of s, and this is another solution. So let's put tildes, y tilde of s tilde. So there are 2 different solutions of the rescaled system, which one corresponds to the original, to the before entering, and another after. 2 of them. So. And then xt will be r of t of s. Remember that we always have this s by y of s. Yeah, so now we will fix. We consider this fixed. Fixed and at the same time fixed, no? T and S still the fixed. So we started at T0 and at certain T. And we want to know what is, where we end if we shrink this region. So where we end, and S tilde is arbitrary, so we can also fix it. So let's fix it to 0. Let's say that S tilde is 0 here. Doesn't matter. You can always, S is defined up to a shift. So what does it mean? It means that, what does it mean for this system? So we have part one. It solves this dynamical system on the sphere under condition that y at 0 is y0, our initial condition here. And then there is certain moment S, some moment of entrance. So there's a certain time of entrance where it enters the regularization region. And we know that whenever we shrink this region, this point will go to 0, because this becomes a blow-up solution. And this time will go to infinity. So what we have is S entrance goes to plus infinity, S nu goes to 0. Because this is what the blow-up means. So blow-up means that in original time we come to 0, but in a rescale time we go to infinity. And then there's part 2. Part 2 is defined by this point. Which means that y at certain point S new solution of exiting time is some value. And then we're interested in the value which comes at 0. So now you see the same consideration. So if you consider any solution which comes to 0, in S it corresponds to S infinity. But if there is any solution that leaves 0, then whenever you approach it backwards in time, S goes to minus infinity. So S exit goes to minus infinity. S nu goes to 0. Now we can put together everything and try to make a picture of all the times to see what happens. So there is a timeline, the original time. It starts at 0, and then there is this time. Then we know with a certain blow-up time, it goes to singularity. And we split it. We put a regularization, so there is a section that we cut from both sides. So there is we regularize the system. So we define this T entrance, and then there is a T exit. They both depend on nu. And then solution is well defined on the full line. Okay, so up to TB, we had the blow-up description in S variable. Right? Which started at 0, but it was plus infinity when you come to this point. So there is one-to-one correspondence. And what we did is we regularized, so we regularize it at S entrance. And this is exactly what I said, that whenever I shrink nu, this point goes to infinity. So this is first, in S variable, up to the blow up, the system has kind of full life. And the same situation is after, but now it's another solution. We're interested in the point T, right? So point T, and we say that we fixed exactly 0 at the same point. So we say that we fixed time that we want to come, and we just let's say that this is 0, and if it's 0, this is S exit. So whenever we shrink it, this goes to minus infinity. So somehow there are two solutions before blow up and after blow up, where the first solution has a full life until plus infinity, and the second solution has a full life from minus infinity. And by regularizing, we cut it. We cut it, so we have some connection. We define the regularization inside, which make a connection between the two. So it takes value at this point and relates to the value at this point. So with this regularization make it jump. It cuts here and make it jump, and then it continues. Okay. So what does it mean? What does this mean? This is not easy to mention. So actually, it's easy, simple, but you have to understand. So look at this. Let us consider our example, which was which was a circle with two attractors. So what happens here is that if we send, so this is nu positive. So if we send nu to 0, S goes to infinity, so we go to attractor. So we went to this attractor A on the left. Now, here, so what we had here, so we fix the initial point and send time to infinity. So we go to attractor. Here it's opposite situation. We fix the time. We fix the final time and put initial condition to far past. So whenever you put initial condition to far past, it means that at that time you are already on attractor. So you put. So somehow what you have. So we're interested here. We're interested in the value y tilde 0 for initial condition y tilde at S exit equals something, which is given by regularization in the limit nu goes to 0 when S exit goes to minus infinity. So if nothing special happens, you see that you give an initial condition far at the past. So if there is a attractor, so if if this point belongs to a basin of some attractor, like say A prime, so another attractor, then in this limit, this point will be exactly on attractor. Belongs to attractor as in the limit. So what it means? So it means that in this case, the attractor that we may be interested in is the other one. So in this case, in our example, is just fixed point. And this is for all times. So what it means, in fact, that whenever you take any initial condition on the left, you blow up infinite time. You regularize in a very, very small neighborhood. And when you shrink, it will live exactly along the attractor. There will be no freedom. So it will be live along the line which belongs to attractor. So this is a line belonging to attractor. So this is a picture. So there are many solutions. There are other solutions like this, but it will always choose this one. There will be no freedom. So whatever regularization you put, doesn't matter. It will live along that. It will live along the attractor, and there is just one attractor which allows you to live. Is this one, and it defines a unique solution. So this is our situation. So you may think of it. This is a bit. This requires some thinking. So essentially, for the conclusion is that if for any, in this example, for any initial condition, x1, x2, where x1 is negative, so for any initial condition of this site, we select a unique solution after blow-up. Which corresponds to this line, x of t equal to the x1 of t 0. So this line. So again, why? Why? Because we entered. Whenever small neighborhood you put, you enter to the small neighborhood, exited somewhere on the right, but smaller the neighborhood, longer the time will be to come to any point. And longer this time, in angular variable, closer you come to the attractor. So in the limit, you will be just exactly on the attractor everywhere. So this is a difference, conceptual difference in this. So for blow up, your behavior near attractor corresponds to large positive times, when after blow up, your behavior corresponds to large infinite time in the past. So this is infinite future, this is infinite past. So whenever you consider infinite future, you just converge to attractor. If you set something at infinite past, you're at every finite time, you're another attractor. So attractor is not anymore asymptotic state. It's exactly the state of your system. So this is, so your observation, recall burgers. Actually, you can make this, at least in a formal way, you can repeat. There is a way to repeat whole formalism by showing that the shock wave is a special solution which is kind of attracting the other solutions. You can make this formalism which is resembling what we did here. So you see, we have a singularity. There are non-unique solutions, but whatever you do in regularization, with the only condition that it should connect the point which comes from the left to connect to the point which comes on the right, it will select just one solution.
So we don't have spontaneous stochasticity?
No, here no. No. This is a deterministic situation which recalls Burger's equation. So, so it gives you two messages. First of all, there can be well-defined limit, and this limit doesn't care much of what is here, how you regularize. So the original system already knew what will happen, because everything is defined by the attractors of the original system. So now there's several immediate extensions. Several immediate extensions. So the first is so if so there can be several attractors. But let's say fixed point. Fixed point attractors. Governing post-blow-up state. So in this case, we had just one attractor, which is defocusing, which corresponds to the solutions which go out. You can have several. And if you have several, then you can, in principle, several possible choices for the post-blow-up dynamics depending on regularization. But at the same time, the situation is rather rigid, because whatever regularization you put, you just will choose from some finite number of post-blow-up solutions. But so the specific form of regularization is still doesn't matter. It's just important to which basin of attraction it will go. So this is the second case. Then there can be different attractors. Non-fixed point attractors. No. Before non-fixed point attractors, let's do something different. Because non-fixed point attractor is actually our goal, because our goal is having attractor which is not a fixed point. The fixed point is Burgers. But before non-fixed point attractor, I want to show you something I think quite curious. Is a spontaneous breaking of time reversibility. So assume that you have a system which is time reversible. So it doesn't matter if the time goes forward or backward, same equation. So how you can do it? So assume that the f of x is such that it's minus f of minus x. So it's an odd function. Okay, so your system has this property. Then you will have what's called PT symmetry. PT symmetry. Parity time. Parity time, it means that parity is a system which reflects x to minus x. And t is what reflects time to minus t. So then you can put them together, which means that pt reflects x to minus x, t to minus t. So it means that the pt symmetry means that if x of t is a solution, of this system dx dt equal f of x, then the pt symmetric version of it, which means minus x of minus t, which is called nu, the pt symmetric. The pt symmetric version of this solution, which is minus x of minus t. So if you invert time and invert x, is also a solution. Just because when you invert x and invert time, you use this property and you see it's already satisfied. So you can change. So it means that for any solution which goes forward in time, you have a solution which goes backward in time. And this minus is rather typical. For example, remember that if you consider the flow, whenever you change time, you also have to change the velocity to minus. No? So this is natural. So whatever. So the Euler equations is a pt symmetric in this sense. So you can whenever you have a solution, formally, whenever you have a solution, you have forward in time, by changing the value, sign of u and changing sign of time, you automatically obtain solution backward in time. So let's see how the singularity breaks this symmetry. And I will just show the one example geometrically. So it in 2 dimensions. x1, x2. And remember, so in 2 dimensions, we have this circle, which corresponds to our scaled system. So now we assume that there are 3 attractors. And we put them here, here, and here. 3 attractors. So there will be 3 repellers. So there will be solutions. So all solutions here go this direction, here they go this direction. Let's put them different color. Here they go here. And so this corresponds to the Fs field. And now we assume that here will be Fr will be positive. So this will be attractor which corresponds to solutions going out. And here Fr will be negative, and here Fr will be negative. So these two attractors correspond to blow up. So whenever you start here, you blow up through this attractor. Whenever you start here, you blow up through this attractor. So you enter to 0. And all exits are below. So essentially, the full picture of the vector field is like this. So you have these attractors and repellers. So they will correspond to the straight lines. So there will be solution like this, solution like this, solution like this, and there will be solutions like this. And then there will be solutions like this. And these are all solutions of this system with a singularity. So you see that whenever you start an initial condition here, you will blow up asymptotically through this attractor, which is this point. Whenever you start in this direction, you will blow up eventually in this direction. So this corresponds to this fixed point. And all the solutions which exit are here. And they will be controlled by this fixed point. So now there is only one fixed point which controls the after blow-up solutions. And we know that the implicit limit will eventually put your initial conditions to far left, which means that we exit exactly on the attractor. And we exit exactly on the attractor means that it will be always, after blow-up, we will always select just a single solution, which is this line. We cannot exit for other lines. Whatever regularization you put here will choose you this path. So you see that there is a duality. From one side, whatever solution you have, whatever solution you have, so your solution will be. So whatever solution you choose, you can make a solution by flipping and changing time. But solution which is chosen is not symmetric, because whenever you start on any point, you will exit on straight line. And the PT symmetric version, it will be straight line and exiting outside. So it's already is not supported. So you see, whatever you put in regularization, it will break the temporal symmetry in a way that you know. So you don't even need to know what happens in the vicinity to know what will be dynamic after blow up, and it's not time reversible. Because why it's not time reversible? Because let's just draw. So imagine you start initial condition x0. So what is the solution? You first blow up. And then we know that whatever regularization you put, it will get out like this. So this is our solution. Its PT symmetric version would be to flip and change the time. So the PT symmetric version of this part will be entering here and exiting there. It's also a solution, but it's not a solution of regularized in the implicit limit. So you see, for whatever solution you take, its time reversal version is not anymore a solution for our system. So in that way, you see that our original system is time reversible formally, but it has a singularity. And we know that whenever we regularize the system and take the limit, it will break reversibility, time reversibility in a way we already know independently of how we regularize, because we know that there is only one attractor which will control this dependence. And actually, this is what happens in Burgers' equation. So it's also Burgers. Because in Burgers, if you consider a solution which blows up and becomes a shock, the inverse is also a solution. It's a shock which collapses and becomes smooth. But it's not admissible shock. So when you change time, you remember that admissible shock in the Burgers which obtained an implicit limit is those that left side should be bigger than the right side. So when you flip it, the left side becomes smaller than the right-hand side. So the inverse solution, time reversible, when you reverse time in the Burgers, you get a weak solution, but it's not admissible. So that's exactly the same situation. So you see that we are with equation which is formally time reversible, but solutions are not time reversible.
This has to do with at some point there's no more unicity. Once those 2 points of these trajectories collapse into the same point, we cannot possibly say where they came from.
Somehow, yeah. You see, somehow I think that it's, as I say, it's a combination of two things. First of all, in order to regularize, you break time reversibility, right? So here inside you break, but then you collapse this region. So somehow you remove it, but at the same time, though you remove it, you remove it, but the system remembers it because you remove something which, in terms of the proper times, it's infinitely large. Whenever, it doesn't matter how close you come to zero, it's still infinite part here and infinite part here. So though you remove this small neighborhood, making it shrinking it to zero, but in terms of the renormalized time, it's always remained infinitely large neighborhood. So there is this interplay between the two situations. I think this is probably good for today. So the next part is the next step will be what we do if the attractor is not fixed point. So fixed point attractor gives us a clear answer of what happens after, because it selects the single solution which just directly corresponds to the attractor of the. But if the attractor is not fixed point, so we may consider periodic solutions. And in this case, we can still understand the limit, but it will be not unique. And the most interesting part is chaotic attractor. So when the exiting attractor is chaotic, see, so if the attractor to which this system is chaotic, and you put initial condition to infinitely far past, it means that whatever you get here is random with a certain probability. So it means that shrinking the regularization, you get a random number with a certain probability. A probability you know. So this is how randomness comes from purely deterministic system. And this we'll see tomorrow. No, tomorrow, no. On Wednesday. No? So I think I better stop here because it's already quite enough information for you to think. Because the next step also will be non-trivial. So here you just try to digest this information by understanding that the difference between pre-blow-up and post-blow-up is a sign of the rescale time. The pre-blow-up is plus infinity, so just approaching the attractor, and a post-blow-up is minus infinity. So your regularization gives you some value at far past. And if you given some value at far past, that at the place where you stay, you're already on a attractor, because there was infinitely large time to approach. And now you can imagine, so if attractor is not fixed point.
So like two attractors, like
In this situation, there are two attractors. One attractor controls blow up, and another attractor controls post blow up. But they're different because these attractors, they're defined by Fs part, spherical part. But also there is a longitudinal part. So this attractor should have Fr negative. No, Fr negative. So it corresponds to solution that attracted to 0. And this attractor should have Fr positive. So it should go. The radial part should be expelling. So here radial part should be focusing, here should be defocusing. So there are two attractors. One attractor, we call it focusing, another should be defocusing. And in the case when the just single attractor focusing, single attractor defocusing, we have a fully unique solution. If there are if there are several defocusing, there can, in principle, can be different scenario for post-blow-up dynamics. And this is known. You can have PD cases which show. For example, in the Burger's equation has this property. So if you regularize it with viscosity in very different forms, absolutely insensitive to how we do it, but it's viscous mechanism, you end up with a shock solution. But if you regularize it with a dispersive term, third derivative, it's completely different solution. It becomes measure-valued solution. So it's kind of almost spontaneous stochastic in a sense. So in the sense, there are several. Supposedly, there are several attractors which can show the post-blow-up dynamics. And next time, so I will show how to see this in ordinary differential equations. So we can just see it in ODE. So thank you, and see you Wednesday.